All right, let's look at a couple more examples. That last one was pretty beefy. I think these two will go a little bit quicker. So this is number 8, bismuth 210. Sounds like a cleaning product, actually a radioactive isotope. And it has a half-life of 5 days. And if you're not familiar with half-life, that's just how long it takes for half of the material to decay. Okay, and so there is a constant proportional growth rate there. So it fits that same formula. And we know that the differential equation that describes that can be solved, or is solved, by this kind of equation. Okay, so the sample originally has a mass of 800 milligrams. And so that's great. We've already got the initial amount. And find a formula for the mass remaining after t days. So we just need to get that k value in there. And we can find that if we have one more point to plug in. And we don't really have one more point. We do have the half-life of 5 days, which means we do really have 2 points. Because we can say at time 0, we got 800. And 5 days later, guess how much we have? Half that. We've got 400. So we do have another point that we can plug in. And by the way, that doesn't mean at day 10 you're down to 0. It actually means at day 10 you have half of that, you're down to 200. And at day 15 you're down to 100, and so on. It always gets cut in half. But we really only need one more point, so let's just use this one. So we can say at time 5, the amount is 400. And we can solve this for k. So start by dividing both sides by 800. And take the natural log of both sides. And we know natural log cancels e, so this will just become k times 5. Divide both sides by 5. And that's where it's time to grab your calculator and figure out what natural log 1/2 divided by 5 is. Let's see, natural log 1/2 divided by 5. It's approximately negative, and this makes sense that it's negative growth rate, right? Because it's actually decaying. Negative 0.1386. So part A, the formula for the mass remaining after t days would be y equals 800 e to the negative 0.1386 t. And now answering things like B and C aren't too hard. For B, say mass remaining after 30 days, so just plug in 30 for time. And I'm not even going to crunch that down. You can do that on your calculator. For C, when is the mass reduced to 1? Now this time we're solving for time. It says when is it reduced to 1? Again, process is pretty similar to what we just did over here. Want to divide both sides by 800 to start. Take the natural log of both sides. And divide by negative 0.1386. If this is all feeling like review from pre-calc, feel free to turn this video speed up to 2x. But in any case, you can crunch that number too. I won't finish crunching that. And for part D, sketch the graph. You can certainly sketch it on your calculator. We basically know what exponentials look like though, right? At time 0, it's at 800. And exponentials eventually flatten out at 0, decaying exponentials like this one. Okay, so that's 8. So let's take a quick look at one more problem. We'll take a look at number 14. 14 is a thermometer that's taken out of a room that's at 20 degrees Celsius. And they take it outside to where the temperature is 5 degrees Celsius. And of course, the temperature on the thermometer starts dropping. So after 1 minute, the thermometer reads 12. And what will the reading be after one more minute, and when will it read 6? So this is Newton's law of cooling, if you're not familiar with that. And Newton's law of cooling says exponential. Newton's law of cooling says get on the right page, and then it's exponential in temperature above the ambient temperature, so above the surrounding temperatures. So really what we have here are some times and some temperatures. Particularly at time 0, at time 0 when they first take it outside, the temperature is 20 degrees, which is, notice, 15 degrees above ambient. So at time 0, 15 degrees above ambient temperature. And then at time 1, it reads 12, which is 7 degrees above ambient temperature. And they want to know a couple things. They want to know what will the reading be after one more minute. So what does it read after 2 minutes? And they also want to know when will the thermometer read 6 degrees, which is 1 degree above ambient. So those are the two questions they're asking right there. First of all, though, we can set up a little exponential equation that describes the temperature on this thermometer. We know that the initial reading, the reading at time 0, is 15. We know there's also another reading at time 1. It reads 7. K times 1, so just K. So 7 15ths equals e to the k. Take the natural log of both sides. And natural log of 7 15ths equals k. So natural log of 7 15ths. So about negative 0.762. So the full version of the model that describes temperature above ambient at any given time is this. So if they want to know what the temperature above ambient is at time 2, say the temperature above ambient It's a multiplication dot, not a decimal dot. The temperature above ambient at time 2 will be that. Let's see if we can. So 15, so e to the negative 0.762 times 2 times 15. So 15 times e to the power, parentheses, negative 0.762 times 2. Make sure that looks right. It does look right. So it should be about 3.3 degrees above ambient. So that's 3.3 degrees above ambient. Keep in mind ambient is 5, so really the temperature after one more minute, 3.3 degrees above ambient plus the ambient, which is 5, is 8.3. So 8.3 degrees Celsius after one more minute. And then when will it read 6, which is 1 degree above ambient? And we'll just take our basic equation, set it equal to 1. And we know how to solve. We've solved this type of equation a few times already. Divide both sides by 15. Take the natural log of both sides. And the time will be natural log of 1/15 divided by that negative 0.762, so we can crunch that. Make sure that looks right, which it does. So about 3.5 minutes, 3.55 minutes. And this is a time, not a temperature, so there's no need to convert it into degrees instead of degrees above ambient. So that's just the answer, 3.55 minutes. And we are done with section 9.4.